Hello everyone, welcome to Technologies Discussion Channel. Okay, today I'd like to continue the discussion on antenna. Okay, so this video, I'm going to concentrate on VSWR, voltage standing wave ratio. So this video, I mainly want to do a quick introduction on VSWR. Okay, the main emphasis will be on the antenna VSWR. Okay, so basically I will explain what are the criteria for an antenna VSWR in order to make this antenna suitable to use, for example, at this particular zone of frequency. Okay, so basically this will be the part 9 series discussion on antenna. So guys, if you're keen to know more about antenna, okay, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on antenna. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you want to have a faster response, you are always welcome to ask me through the comment. Guys, also, okay, please give me some feedback so that the quality of this channel can be further enhanced. Okay, before I continue, okay, I'd like to urge you guys to help this channel by pressing the like button. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for your strong support. Okay, so these are the key parameters of antenna. Okay, I have done all this discussion. Okay, mainly I have discussed on radiation pattern, the gain, directivity, beam width, polarization, and antenna impedance. This video, I'm going to concentrate on this VSWR, voltage standing wave ratio. Okay, the rest I will do in a later video, okay, on the antenna discussion. Okay, firstly, let's do a quick comparison between standing wave ratio and voltage standing wave ratio. Okay, so basically over here, you will be able to understand the key difference between these two, SWR versus VSWR. Okay, let's come to the standing wave ratio first. Okay, so this standing wave ratio, they actually measure the impedance matching between a load and the characteristic impedance of a transmission line or waveguide. Okay, so basically this standing wave ratio basically measure, okay, how well your impedance matching is, okay, between the load. Okay, for this case here, the load will be the antenna and also the characteristics impedance of a transmission line. So basically you can imagine a transmitter, okay, basically connect to the antenna with the help of a coaxial cable, for example, for this case here. Antenna will be the load, okay, the coaxial cable will be the transmission line. So basically this SWR, okay, they actually measure how well the impedance matching is between the load and also the characteristics impedance of the transmission line. The impedance mismatch create standing wave along the transmission line, and SWR can also be defined as the ratio of the maximum amplitude to the minimum amplitude. So basically, in short, SWR equals to amplitude maximum over minimum amplitude, okay, of the transmission line. Okay, so basically this can be also measured by current. Okay, for example, the maximum current, okay, divided by the minimum current can be measured by electric field strength. The maximum electric field strength over the minimum electric field strength can also measure by magnetic field strength, maximum magnetic field strength over the minimum magnetic field strength. So basically, this is the definition of SWR. In short, okay, basically you can see over here, okay, they can be in terms of amplitude, in terms of current, in terms of electric field strength, and also magnetic field strength. Okay, this voltage standing wave ratio, VSWR, is mainly specifically refer to the ratio of the maximum to minimum voltage on a transmission line. Okay, so basically now you know voltage standing wave ratio mainly concentrate on describing by using the maximum voltage to the minimum voltage basically on a transmission line. A VSWR of 1.2 can indicate that the peak voltage is 1.2 times the minimum voltage along the line, okay, provided the line is at least half of wavelength long. So basically this will be the distance from the antenna. Okay, so like what you mentioned here, the length of the antenna must be at least, okay, half of a wavelength long. Okay, so over here you can see that this will be the Vmax, this will be the Vmin. So basically over here it indicate, let's say we indicate that VSWR is 1.2. Okay, so therefore Vmax is equals to 1.2 multiplied by Vmin. Okay, so basically this is a very simple definition on VSWR. Okay, when there is a mismatch between the load impedance and the transmission line, okay, a portion of the forward wave sent towards the load is reflected back along the transmission line towards the source. Okay, so when we actually have a different impedance, okay, which means that the impedance for the load and also the transmission line is not the same. Okay, so therefore, okay, we actually have a portion, okay, basically all the wave will be forward wave. Okay, however, because of the mismatch, slight portion or can be all the forward wave will be so-called sent back along the transmission line. Okay, so later on I will explain this again, okay, with this diagram. But at this moment you can see from here, okay, a portion of the forward wave sent towards the load, okay, is reflected back along the transmission line towards the source. Okay, as a result, okay, the source experience an impedance different from what is being expected, okay, because you actually have the reflected wave, and because of this, your impedance actually varies. Okay, so therefore this can be led to, okay, most of the time will be less, but in some extreme case, okay, more power will be able to supply. Okay, but typically less power will be supplied. Very rare can be more power can be supplied. Okay, the outcome is highly sensitive to the electrical length of the transmission line. Okay, so let's take a look on this animation to understand better. Okay, so the blue wave, okay, will be the incident wave. As you can see here, okay, the blue wave will be the incident wave. The red color wave will be the reflected wave. Okay, so if you look at the blue wave, you can see that the blue wave actually move towards the right. Can you see over here? You can see that the blue wave actually move towards the right. Okay, as for the reflected wave, which is the so-called the red color, okay, you can see that they actually move to the left. Can you see here? So basically the incident will be the blue, the reflected will be the red. And this is basically, let's say this will be the load here. So I actually have a forward wave and I also have a reflected wave. Okay, over here you can see that all the wave so-called will be reflected back. So basically this will be in the situation when it is actually a short circuit, okay, at the end of this transmission line, okay, which means that over here there will be a short circuit. Okay, so over here you can see that the outcome is actually the black color. Okay, so why this is called a standing wave? Okay, because you can see that the black color wave, they don't actually move. Okay, as I mentioned earlier on, the blue color, you can see that they actually move to the right, and the red color, they actually move to the left. But the black color, you can see that they are actually stationary. Okay, so therefore, this is the meaning of standing wave. Okay, because they don't move as compared to the incident and reflected wave. Okay, so basically, this example illustrates, okay, all the forward wave will be reflected back, and therefore later on you will see that actually for this case here, the reflection coefficient will be -1, and the VSWR will be equals to infinity. Okay, so later on you will be able to understand this. But at this moment, okay, I just want to quickly explain this chart to let you understand on VSWR. Okay, so next, the last slide for this general VSWR. Okay, in order to achieve a good VSWR, okay, it actually requires impedance matching. Okay, so basically you can see that this will be the matching network. Okay, in order to achieve, okay, maximum power transfer, okay, we need to have some form of impedance matching. Okay, the impedance matching occur, okay, when the source impedance is the complex conjugate of the load impedance. So basically, in short here, so if they are actually complex conjugate, which means that one will be the positive, let's say the imaginary part, the other one will be minus. And because of this, basically the imaginary part will be removed away. Okay, so therefore, in order to remove the imaginary part, okay, we need to have a complex conjugate. Okay, so basically under this case here, okay, when the source and the load, okay, basically they will have some function of complex conjugate, then I will only left the real number. Okay, so the easiest and most effective way to achieve this, okay, and in order to minimize the losses along the transmission line, is to ensure the imaginary part of the complex impedance of both the source and the load is 0. Okay, so definitely we are not able to change the, let's say, the imaginary part of the antenna. Okay, as for the source, let's assume that we can't change any of them. So in order to resolve the issue is basically we need to cancel away the imaginary part. Okay, so if we cancel away the imaginary part and we left the real, so-called the real term, okay, or the so-called the impedance, what happened over here is this will be 50, and if we decide to look into here will be 50, then we will ensure to have a maximum power transfer. Okay, so over here in another word, okay, both should be pure resistance value, okay, which is equals to the characteristic impedance of the transmission line. Okay, so therefore the transmission line, let's say is 50 ohm, everybody all designed to the 50, and therefore we can assure maximum power transfer. Okay, so basically this will be the last slide to have a general idea on VSWR. Okay, so this slide is onward. Okay, I will focus on the reflection coefficient. Okay, I need to quickly go through this reflection coefficient so that you have a better understanding on VSWR. Okay, the voltage component of a standing wave in a uniform transmission line consists of the forward wave, okay, with this amplitude, which we denote as VF, superimposed on the reflected wave, okay, which we denote as VR. Okay, so this is the forward wave or incident wave. This will be the reflected wave. Okay, a wave is partly reflected when a transmission line is terminated with an impedance that is not equal, okay, to its characteristic impedance. Okay, the reflection coefficient, okay, can be described, okay, as shown over here. So either one of them, you can actually describe the reflection coefficient. Okay, so this reflection coefficient, in fact, is a complex number, okay, which means that they consist of real and imaginary number, okay, that describe both the magnitude and the phase shift of the reflection. Okay, remember this is a reflection coefficient, so this number actually describe how much will be reflected back in terms of the magnitude and also in terms of the phase, okay, which most of the time in degree. Okay, the simplest case with the reflection coefficient, okay, measure and the load, okay, there will be three conditions. Okay, so one will be the reflection coefficient as -1. Okay, this is when the line is short circuit. Okay, where we have a complete negative reflection. Okay, when we actually have this reflection coefficient equal to 0, which means that there is no reflection. Okay, which means that the line is perfectly matched. Okay, so over here you can see that this case here, when these two are equal exactly, then I will have the so-called equation of equals to 0, which means that there is no reflection, which is the scenario that the ZL equals to Z0. Okay, so when reflection coefficient is equals to 1, okay, so therefore the line is actually open circuit, which means that it will be a complete positive reflection. Okay, so earlier on I mentioned on the end of the short circuit, okay, all the waveform will be reflected back. And for this case here, when the line is open circuit, all the wave will be so-called forward moving. Okay, so basically this is a simple description, okay, on this reflection coefficient. Okay, voltage standing wave ratio actually indicate the level of mismatch between an antenna and the feed line connecting to it. Okay, VSWR is always a real and positive number for antenna. Okay, so VSWR, okay, most of it won't have any imaginary number, and it will be a positive number. Okay, so in some scenario, okay, where you have other units that are not VSWR, but they have so-called real and imaginary part, and some number can be positive and negative. Okay, but for VSWR, it's always a situation that it only has a real number, and it also will be a positive number, mainly for this antenna. Okay, the smaller the VSWR, okay, the better the antenna. Okay, so basically this discussion, okay, again, I like to fall onto the antenna VSWR. Okay, so earlier on I have briefly described on the VSWR. So this video mainly I will be discussed on this antenna VSWR. Okay, so like I mentioned earlier on, this VSWR can be a very clear indication, okay, how well we actually match the antenna, okay, with the feeding line or maybe the transmission line, okay, in between the antenna and the transmitter. Okay, so this VSWR will indicate how well is the impedance matching. And I mentioned earlier on, for antenna, VSWR is always a real and positive number. The smaller the VSWR, the better the antenna. In short, the smaller the number. Okay, not really the smaller the number, okay, but the minimum is actually equals to 1. You will be able to see that later on. But in short, okay, the smaller the number, which means that closer to 1, okay, the better the antenna. So how close you equals to 1, okay, cannot be lesser than 1. Okay, 1 is the smallest number of VSWR. How close you are actually towards the 1, okay, which means that how well the antenna is actually matched to the transmission line, and the more power is actually delivered to the antenna. Okay, VSWR range from 1 to infinity. Okay, so minimum is 1. Okay, infinity, which means that it's chaos. Okay, you can't use this antenna for this so-called region here. So therefore, as I mentioned here, the key idea is to have the VSWR as close to 1 as possible. But keep this in mind, 1 will be the minimum number. Okay, cannot be 0.9, etc. So 1 will be the minimum number. Okay, in this case, okay, no power is reflected from the antenna. Okay, which means that when VSWR is equals to 1, okay, all the power will be forward. Okay, no power will be reflected from the antenna. Okay, a VSWR value below 2 is in generally considered quite good, okay, for most antenna application. Okay, this indicate a good match between the antenna and the feed line. Okay, so when you actually have a VSWR, okay, which is below 2, okay, in fact 2 is a very harsh number. Okay, but let's take it that, for example, for VSWR, which is below 2, which means that it's actually well matched, okay, between the antenna and the feed line. Okay, when someone say an antenna is purely matched, okay, it often means that the VSWR exceed 2 for a particular frequency of interest. Okay, return loss is another important specification to consider. Okay, so maybe on my next few video, okay, let's find an opportunity to discuss about return loss on antenna. Okay, as the VSWR increase, okay, more power is reflected. The higher the VSWR, more power will be reflected and less will be transmitted to the antenna, okay, which can negatively impact its performance in several ways. Okay, firstly, okay, if we are going to have a big VSWR, okay, so which means that, okay, a lot of power will be reflected back. And when we actually have a lot of power that is actually reflected back, then we will reduce the transmission power. More will be reflected back, okay, lesser will be transmitted out from the antenna. So therefore, with this kind of high VSWR, we actually have a tendency to have a reduced transmission power. Okay, the most immediate effect of a high VSWR is the reduction in the power transmission by the antenna. Okay, when power is reflected back towards the transmitter, it may be absorbed or cause damage, leading to a decrease in the effective power output. Okay, the higher the VSWR, the greater the power reflection, which can significantly diminish the antenna performance. So in short, okay, if the VSWR is so high, okay, the antenna actually become it's not not possible to radiate out any form of power. So in short, in order to meet the antenna to work at certain desired frequency, okay, we need to ensure that VSWR as close as possible to 1, but not smaller than 1, as close as possible than 1. Okay, increased noise. A high VSWR can also elevate the noise level that will be received by the antenna. Okay, the reflected power can interfere with the incoming signal, okay, introduce noise and reducing signal clarity. Okay, this issue is particularly concerned, okay, if we use antenna in a sensitive application, okay, such as radar or radio astronomy. Okay, so radar is basically, just imagine the signal sent kilometer away, and the reflected wave, in fact, is very weak. So any form of noise can actually so-called damage, okay, this kind of information. So therefore, in a very sensitive application such as radar, okay, we will want to minimize the noise as possible. Okay, so if we want to reduce the noise, okay, one thing is we need to keep the VSWR as low as possible. Okay, so basically this will be under this antenna VSWR. Okay, earlier on I have also quickly mentioned about the damage to the antenna or transmitter when we actually have a high reflected wave. Okay, in some severe case, okay, a high VSWR can damage the antenna or transmitter. In short, okay, instead of forward wave, okay, everything all reflected back. And this reflected wave can be very harmful, okay, for the transmitter, okay, or even the antenna itself also. Okay, the reflected wave may cause excessive voltage and current on the transmission line. Okay, this may lead to overheating and component failure. Okay, the risk is higher with high power transmitter or antenna operate at high frequency. In short, okay, if we're going to have a high power, okay, for example, we transmit 4G signal, 5G signal, basically they actually utilize high power. And because of this, okay, a high VSWR can be an issue. Okay, in general, a VSWR of 2 is equals to 1, okay, or less is considered acceptable for most application, which I have highlighted earlier on. However, for certain critical application, okay, a VSWR of 1.5 or even 1.2, okay, may be required. Okay, so in certain niche area, okay, we want to have the VSWR as small as possible. So even as small as up to 1.2, okay, may be required for certain critical application. Okay, often in industry, okay, antenna are actually screened, okay, whether they pass or fail, okay, based on VSWR. Okay, so basically, in short, how to quantify your antenna performance will be by VSWR. Okay, so this is a method of measuring the antenna passively to determine if they are properly tuned in a quick manner. Okay, so the antenna is measured with a network analyzer, and the VSWR as a function of frequency is recorded. Okay, so basically, if you have this network analyzer, you can actually measure your antenna, okay, VSWR versus frequency. And from here, you can actually determine whether this antenna is able to operate in this frequency region. Okay, let's take a look on the example to understand better. Okay, so over here, you can see that there are actually two antennas, one in blue, one in silver. Okay, so in the graph, okay, we see the VSWR measure for two antenna. Okay, for this test, okay, the set of specification for passing, okay, will be less than 3. Okay, which means that VSWR need to be lower than 3 in order to pass. Okay, we see that the VSWR measurement for one antenna, okay, which is the silver line, they are significantly higher than 3, okay, across certain frequency. You can see that this will be the limit line. For example, here will be 3, VSWR of 3. You can see that this frequency zone, they are actually more than 3. And you can see over here at the end here, this part here is also more than 3. So this is what it means here. Okay, so they actually have some significant higher than 3 across certain frequency. Okay, therefore fear the unit, which means that this antenna is not suitable to operate in this frequency band. Okay, the VSWR for another antenna, which is the blue color, okay, they always remain lower than 3 across all frequency. Hence, it is suitable for this intent use. Okay, which means that the blue one, okay, actually will be suitable to use the frequency, okay, in this zone here. So basically, from here you can see that how can I actually select the antenna will be by the VSWR. Okay, as I mentioned earlier on, it need to be as close to 1 as possible. Okay, so if not, okay, most of the time for industry practice, okay, we will either set it to 3, or maybe some of the case we actually set it to 2. So if they are lower than 3 or 2, then the antenna will be seems to be suitable to use. Okay, let's quickly understand a few distinct value of VSWR. Okay, so when it's 1:1, okay, which means that VSWR is equal to 1, it means that it's actually a perfect match. Okay, there won't be any reflection at all. Okay, if we have this situation 1.5 VSWR, it's still considered a very good match. Okay, in fact, it's extremely good match. Okay, there will be some reflection, okay, but this typically will fall under the acceptable performance. When it's 2:1, okay, again, this form here is still acceptable, okay, but some loss of power and increase of noise, which I have described earlier on. Okay, anything more than 3 or at 3, okay, it considers already quite a poor match, okay, but most of the time we can still tolerate with VSWR of 3, okay, but we want to avoid, but in some case here, this is actually classified under poor match. Okay, significant loss of power and increased noise. Okay, if anything that is in fact more than 3 is considered is not feasible anymore. Okay, so this form here is actually a very poor matching network. Okay, and you are going to have the risk of damage to antenna or transmitter. Okay, as you can see, okay, VSWR is an important factor to consider, okay, when we actually design or operate in an RF antenna system. Okay, when we actually design the RF system, okay, when we actually want to work in certain frequency, okay, we need to study the VSWR. They need to be at least, okay, typically about around less than 2. Okay, by keeping the VSWR low, okay, you can ensure that your antenna is operating at maximum efficiency and you are not wasting power or introduce noise. Okay, so basically this is what we have for today. Okay, so with this, I'd like to end my discussion. Okay, please help to like and subscribe. Once again, thank you so much for your strong support. I hope to see you guys soon. Bye for now. Thank you.